Hi, Noah.
Hi.
So, how did you make out with the questionnaire?
I rewatched the video that Greg put on his YouTube channel, so I just went through the lesson and followed along with those questions. And I think I understood all your explanations. I guess we'll see as we go on, but yeah, I just went through that.
Okay. Any big? I have no clue what they're talking about.
No, but
Okay.
if I remember one, then I'll ask.
Yeah. 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 Good. So, do we have Reg on? I don't see him right now. So the video, did that turn out okay?
Yep, it was
hmm
very clear.
hmm Well, we'll try to do our own video tonight. Well, last one it didn't record the sound. Everything was okay, but then the sound is really what's important. But we're still missing a few people. So we're still missing Greg, Reg. There's Greg. Hi there. Hey, Greg. Can you hear me?
Can you hear me?
Yes, we hear
Oh,
you.
perfect. Good. Sorry, I had trouble finding the link again. Holy shit, my own stupidity.
Yeah, I think all you need to do is go into Google Meet or so, and it will pop up, or it should pop up. You're
Yeah,
able.
I'm sorry. I was looking for Zoom. That was my fault.
Or yeah. I'm much better on Zoom than on this stuff.
Yeah. So
That's for
I
sure.
yeah.
So Jimmy is actually there. And so we're missing.
Back in 2 seconds.
Ray, I think. Yeah. Ray, are you there? Oh, there's Ray. Hi, Ray.
Hello. Can you hear me now?
Yeah, I can hear you. Yeah.
Yeah, I had a hard time connecting up. I didn't get an invitation, and
Oh, really?
yeah, so I had to get my wife to do it for me.
Yeah, it should also show up in the Google Calendar.
In the witch calendar?
In the Google Calendar. So if you
Yeah,
just
I looked, I couldn't find it anywhere, right? And I even thought I'd look back to see if I could find an old invitation, but
yeah. I basically. Oh, there's Reg. Okay. Hi. I basically set up these meetings all the way into December on the Google Calendar, so it should be there.
yeah, well, I usually get an invitation, it shows up, even a couple of days before, but I
Yeah.
didn't get I didn't get
Okay.
anything this time.
Oh, okay. Okay, well, good to see you all. Now, the last time we had there were a few things where there were questions about it, or I think where there were some things where people weren't really clear about. And before we go into the next set of questions, we want to go through that. And I'd ask you all to mute your microphones. And then if you have a question, of course, just unmute and blurt it out. Okay. So, Greg, yeah, you're muted. Excellent. Okay, so one of the things we talked about last time was air brakes and spoilers and this kind of stuff. So I'm going to share. We're doing a. Oh, no, wait a minute. We gotta record this. Okay, we record. Okay. Okay, we should be recording now. And you're still all there, which is a good thing. And I'm going to share. Are you? Yeah, you're still all normal. Today I'm going to share an entire screen. That sort of cuts down on the time between changing windows. Okay, so you should see this. This is out of Mark McDermott's a PowerPoint. And remember, we were talking about dive brakes versus spoilers. And I said we use them colloquially interchangeably. So we sometimes call our dive brake spoilers and so on. But a spoiler is really, if you look at this here, if you can see my cursor there, that is a spoiler. So airliners have those. And a spoiler is hinged at the front and just sort of stands up in the back. In the old days, gliders like 126s and so they had spoilers like this. They're not very effective, so that's why we don't use them anymore. And air brakes or dive brakes is what we have today. They are basically boards that pop out of the wings. They can pop out the top and the bottom. For example, the Puchacz had upper and underside air brakes, super effective. However, it is actually from an aerodynamic point, it's easier to make a high performance wing if you only pop them out on the top, right? And that's why in the modern airplanes, they're not going out, they're not coming out both sides anymore. But in the old days, they did, and they're quite effective. Okay, any questions to those? The other thing we talked about a while ago were the axes of an airplane. And so you see this model here. And so we have the longitudinal axis. It runs basically, it's the along the center of the fuselage. You'll see that one. Then we have the axis that runs along the wings, which is the lateral axis. And then we have what we call either the z-axis or the normal axis that goes it's vertical. It's a vertical axis. And what we do is around the longitudinal axis, we roll. Around the lateral axis, we have pitch. So we change the pitch. And around the normal axis, we yaw. So when we use the rudder to yaw, then we turn the plane around the normal axis. Any questions to that? Or is this clear to all? Okay, because that kind of stuff, a lot of these terms come up in the exams, and then if you don't know what the term means, you may lose some points. And that's actually something that has, most of these questions have no relevance to real gliding, but that's one that has relevance to real gliding. Okay, and then we can move a little bit down here and go into this one. And that shows you the forces acting on an airplane. So the weight goes straight down. The lift is actually perpendicular to the airflow. So it's not directly opposite to the weight. It's actually going a little forward. and then the thrust is pulling it along. In our case, it's basically like going sliding downhill, like a sled down a track, and the drag is opposite to the thrust, holding it back. Okay, so I guess this is all we want to show here. So we'll put this back. And so gotta take a quick look what else I wanted to show. Okay, weather. Yes. I'll make this big. Remember, we had the question how the highs and the lows turn, and do we still remember how those work? Which way does the low go?
Counterclockwise.
Counterclockwise. Excellent. Yeah.
And into the low.
And into the low. Yes. Do we know why these things are turning? Do we remember that?
Yes, because we've watched an episode of The Simpsons called Bart versus Australia, which explains that the rotation of the Earth makes things turn one way in the northern hemisphere and the other way in the southern hemisphere.
Yes. Do we know the name of these forces that make this happen? They're called.
Anybody except me?
Yeah. Well, anybody else? Nobody's speaking up. So, Reg, you have the floor. Coriolis. I'm not sure if it's Coriolis or Coriolis.
Okay, Coriolis.
Yeah. In German, they would say Coriolis. But anyways, so these are called the Coriolis or Coriolis forces, and they happen if something is moving on a rotating surface. There is actually an excellent video about this. It's really good. I'll see if I can bring this up. But before we go there, let's look at our weather systems. So here we have a low, and around the low we have isobars. Do we know what an isobar is? An isobar is a line of equal pressure. ISO is always equal, right? So the isobars, the low has the lowest pressure, and then around it there is a line with a slightly higher pressure, and then there's another line further out with even higher pressure. And these are the isobars, and they're in weather charts as well. And the rotation around the low is, as we said, is counterclockwise. And then there is fronts in the low. There's warm fronts, so there is basically warm air going in there because air masses mix typically in low pressure systems. And then there is a cold front. So usually, well, all the time, usually the warm front runs ahead of the cold front. But the warm front is the cold front is faster than the warm front, and eventually it will catch up. And both of them turn around like this around the low. And oops, okay, I didn't want to go there. Maybe. Okay, so fronts are boundaries between different air masses, and they pass over us as these air masses move like currents in an ocean. If you read my weather reports, quite often I'm saying, well, a cold front is passing through overnight, or a warm front is passing through, that kind of stuff. The other night we had a warm front with, at least in New Hamburg, pretty severe thunderstorms right during the night, which is very unusual this time of the year. So a cold front is cold, heavy air, and it displaces the warm air at top. So it moves. Let me go one further. It comes in like a wedge, and there's the warm air, right? And it sort of runs under the warm air and pushes the warm air up. And what happens there is actually that's pretty violent when that happens. So what we get is thunderstorms and all these things, right? You see these clouds. I'm not sure how they come through. They should, yeah. That's what you will see in a cold front. It'll come in, very impressive clouds, thunderstorms, pretty violent weather. The winds will actually the wind will switch further. When you look into the wind, will switch to the right. Do we remember what that's called if the wind switches to the right? Or if the wind turns counterclockwise? It's called the wind veers. Remember that? And that's also a question in the. And if the wind goes the other way, it's backing. So if the wind changes in a clockwise direction, so let's say it's from 270 to 230 or 210, that's backing. If the wind changes from 270 to 300, that's veering. And when a cold front comes through, the wind usually goes from slightly southwest to northwest, so it veers. That's your typical cold front passage. What you see in a cold front is first of all violent weather. The wind changes eventually, temperatures drop, and then pretty soon it starts clearing up after the front, and about 18 hours or so. 18 to 24 hours after the cold front passed, we can have pretty good soaring conditions because the air mass, the cold air mass, that came in is very convective. And that's really going closer to the passage. The cold air is simply too shallow to give us good thermals. This could be 1,500 feet or something off the ground. It's too shallow to do anything with, but the wedge is getting thicker, and then so about 1.5 to 2 days after, we probably have pretty nice, like 4,000 or 5,000 feet thermal tops. The thermals can only rise to this blue line because above it is still warm air, and the blue line basically is also an inversion line, which means the temperature with altitude actually rises for a little while, and that stops all the thermals go away here. Okay, any questions to that? Then let's have a look at a tephigram. So this would be a typical low-level tephigram, low in the atmosphere. And what we see here is temperature over altitude. And what happens is early in the morning, the ground is still cold, and it actually cools the surrounding air. That's why there is a layer, maybe 500 feet thick, where the temperature actually rises as we go up. And as long as you have this, there's no thermals. Then this is the normal, what we say is the lapse rate. So basically the air temperature reduces or declines with increasing altitude. And then there is another inversion, and that inversion is the top of the thermals. So if we go a little further here, that would be the natural, that would be sort of the average lapse rate, but let's see if you see something else. Here is the inversion. This is the ground inversion, which eventually when around 11 o'clock, this will heat out and disappear. And these are lines that show how an air parcel that takes off from the ground, how it cools. And the reason why it cools is not because it's in cooler air, it's because it's expanding, and expansion, when air expands, it always cools. And that's also a lapse rate. That's the dry adiabatic lapse rate. That's about 3 Celsius per 1,000 feet. So even if during the midday here at 25 degrees or so, an air parcel goes up, it keeps going up. It's still warmer than the environment because this is the environmental temperature. but then it hits this point, and at this point, the air parcel is cooled, and the environmental lapse rate has basically reversed because it's an inversion, and this is where the thermal stops. Inversions are good or bad. Number one, they stop our thermals. That's the bad part. But the good part is if there's no inversion, the thermals would go up to 40,000 feet and develop huge thunderstorms. So if there's no inversion, this is when you see these huge towering queues at perhaps 11, 12 o'clock. And by 2 o'clock, you have a huge thunderstorm that goes all the way up to 40,000 feet. People sometimes ask me, well, why do we have inversions? Is this good or bad? Well, they're good and bad. Okay, let's go a little back here. The lapse rates. So we have the environmental lapse rate. This is the average rate at which the atmosphere cools. It's about 2 centigrades, 2 degrees Celsius every 1,000 feet. That's sort of indicated in here. And as we go up higher, it follows about that line. But low to the surface, we have also, there's heat exchanges and the air is bubbling. And so if we look a little closer, we have, it deviates a little bit from this is an average, the standard atmosphere average. But it's about, we should know it's about 2 centigrades or 2 Celsius per 1,000 feet. Then we have the dry adiabatic lapse rate, which is in the tephigram represented by these blue lines. And that's about 3 degrees per 1,000 feet. And going back. And then there's also, when it forms a cloud, then we have the wet adiabatic lapse rate, which is only 1.5 Celsius per 1,000 feet. So basically, what happens then when we have a cloud, that with increased altitude, the air, actually the condensation releases energy, and that's why the temperature stays higher. And with a cloud, it could actually go around that. Sorry for that. Hope that stops soon. Hello? Canadian Tire Bank. Excuse me, I was setting up my phone today and I thought it was the guys from Fido calling me back. This looks like the same number. Okay. So when there's a cloud forming, then this lapse rate will go much steeper. I'll see if we have a cloud in this. No. Okay, I go back. So let's go back to our cold front. So here was our cold front there. And we're coming in here. And this would be the inversion we have just seen in the tephigram. Okay, so now let's look at the warm front. So we have nice cool air with good gliding conditions over us. And now a warm front comes in. And since warm air is lighter than cold air, it's the warm air sort of sliding up on the cold air. The cold air is like sort of a water puddle. It's pretty dense, and the warm air just moves up. And the typical clouds we see is, first of all, we see these high cirrus and altocumulus clouds, basically layered clouds. Here more, and then they get thicker as more warm air comes in. And also displaces the cold air. So it all starts up here at maybe 20,000 feet, right? And then as this line moves this way, we're getting lower and lower. So these are already lower clouds and denser clouds, altostratus, something like this. And in the end, when the warm air is pretty much close to the ground, you see a pretty dense stratus and quite often rain. And the warm fronts are slower than the cold fronts, right? I said this earlier. And therefore, this bad weather that comes along with a warm front can last for a few days. And even in the early stages of a cold front, when cirrus shows up, as far as gliding is concerned, it's not good. We don't like that. It's not really right away. The cirrus filters quite a bit of sunlight, sometimes 30-40%, right? And this is energy we need. It's energy and it gets reflected back into space instead of helping us fly better. Better means higher, faster, etc. Okay, then we look at a weather map. That's your typical weather map. There's the highs are always blue if it's colored, and big H stands for high, a big L stands for low. The lows are red, and there's some stationary fronts. A stationary front is shown where it's where cold and warm fronts. This is a piece of a warm front. That's like a warm front here. Basically are not moving, so that's why it's called stationary. So to the back side it looks like a warm front. To the front side, which is here, it looks like a cold front, and meaning the sucker doesn't move at all. So this is what a real cold front looks like. And from the way the air flows from the high, we know it's around the flow around the high is clockwise. It flows up into this low. And now you may wonder what this is like compared to this. So the blue things with the little pointy ends there, they're cold fronts. Like here is a cold front, right? The red pieces, red lines with a knob up front is a warm front. And this is, this magenta color is basically the point where the cold front has caught up with the warm front. And what happens, it lifts the whole front thing up in the air, and it's called an occluded front. So first there was a warm front and a cold front, and the cold front has caught up, and now it's occluded. Same thing up here. Here it's still a cold front, but this one has already occluded. So there's basically there's cold fronts, warm fronts, and occluded fronts where the cold front has caught up with the warm front. Okay, and that's basically everything about fronts. I don't think so. Here, hey, questions. Any questions to this? So in the exams, you will probably you will get questions. What is a cold front, or what is the passage of a cold front? How does it look like? And that kind of thing. For that, you need to know what a cold front is, right? I don't think there's any questions to an occluded front, but there could be a question like, what happens if a cold front catches up to the warm front? And this is where the term occluded front comes in. Okay, then we'll end this and make it go away. Yeah, sorry for that phone call there before. Okay, so we also talked about the lapse rates in the tephigram. And then we talked about area forecasts, terminal forecasts, and METARs. Remember that the last time? And I want to show you what they kind of look like. Okay, here we go. So this is the new NAV Canada thing. There's here weather. You can look this up too. And let's say we want to look at the TAFs and the METAR for Kitchener. And let's say we take Hamilton as well. Okay, and then we say we don't want this, we don't want this, we don't want this, we want METAR, we want TAF, we don't want the pilot reports, and we don't want upper winds. And we go zippity doo, and there it is. And it's all in code. So one of the things I'm going to send out to you is a code decoder that shows you examples of forecasts, METARs and TAFs, and it explains what's what. So what we read here, the METAR, do we remember what a METAR is? A METAR is an observation, a point observation. And this is all. It's not a forecast or anything. This is basically saying this is the weather we observed at on the 15th at 000 Zulu. And auto stands for automated observation. So this was not a person looking at this. It's basically a computer that measured all this. And it says visibility is 8 miles, and this is actually statute miles, land miles, the good old American type miles. Terrible that they use that, but that's what they do. The minus always means light. So light rain, RA is rain, and overcast at 024, that means 2,400 feet. There's basically overcast conditions. And the temperature is 5, the dew point is 3 Celsius. So basically that means that the temperature is really close, and this is actually the METAR for right now. So the temperature is really close to the dew point, which means it doesn't take much to develop fog. Just needs to drop a little more and it will be fog. It's 2 degrees apart still, but if it's sort of within 1 degree or so, you should expect fog. And then there's a remark, there's precipitation at half a mile. 0.5 millimeters in the past hour. And this is the pressure here. So that was the METAR at 0 Zulu. So 15 is the date, and this is Zulu time. So in Zulu time, it's already it's now 0 and 30 minutes, 5 hours now in winter, 4 hours in summer. Zulu time, there's no summertime. That never changes. And so this is the date, this is the time, and this is what they measured exactly in Kitchener at that time. Hamilton, pretty much the same thing, right? Oh yeah, and the wind, they measured in Kitchener, 120 degrees, so east-southeast at 5 knots, pretty light. And in Hamilton, they actually have northeasterly winds this is because of the lake, at 6 knots. Okay, so this is the METARs. That is a point observation at a certain time. It's not a forecast. The forecasts are those. There's a TAF, stands for Terminal Forecast for Kitchener, and it gives you the time when it was issued on the 14th, so November 14th, at 23:37, so just before midnight Zulu. All the times are in Zulu. So that was about 6-ish local, 6:30 local. And it says here between on the 14th, between 23 and the 15th 01. You should have reasonable visibility, +6 miles, light rain, overcast at 1500. Then from 15:01, which is basically 8 o'clock local time now, you have wind 100 degrees, so basically easterly 0.6 knots. visibility +6 miles, light rain, overcast at 1500, and so on. So this is the forecast, and it goes all the way through until the next forecast is to tell you when the next forecast comes through. So the important thing to remember, because there are questions about this, is METARs get normally issued every hour. Every hour there's a new METAR. Unless there is really rapid change, then they issue METARs in between as well. And so they're every hour or earlier. The terminal forecasts are issued every 6 hours. And the area forecast, an area forecast would cover all of Ontario and Quebec. It's usually a chart. It's not a story. And those are issued every 6 hours. Area forecast and terminal forecasts. And you may get questions like a little bit of a tough, what does that mean, right? So we have to familiarize us a little bit, and I'll send you tonight after we are done, I'll send you sort of the decoding sheet for that. I'll send that out, attach it to an email. Okay, any questions to that? I'm hearing none. Then the other thing we had last time was, remember the crosswind diagram for crosswinds? So we put this one up here, make it big. So this is a typical diagram. This would be the direction of the runway. And then you decide which way, what the angle of the wind is. So if your runway is 27, and this is 27 magnetic, remember all the runway numbers are 27, and the wind is 300 magnetic, that would mean that the wind is 30 degrees to your right. So this would be the case right here. And if it says, if it's 30 degrees to your right, you can basically take the 30-degree line here and wander down. And if it's 25 knots, which in this case it is, there you stop. If you go over to this axis, then it gives you the headwind component you have when you land on this runway, which is still over 20 knots, right? It's not much less. If you go down to this axis, and this is this one, then it gives you the crosswind component from the right you have. And then you can, this is 10, this is 20, so it's about 13, which for a glider is still quite a bit, because a glider is typically, the demonstrated crosswind component is around between 10 and let's say 12 knots. So demonstrated means you can fly with higher crosswinds, but there's no guarantees. You're on your own. And the demonstrated crosswind component is in the manual of the newer gliders, not of the real old ones. But if you look at the manual for example, of the DG 1000 or the Duodiscus, or also the X-ray and Yankee Juliet, you'll find these things in those manuals. Papa Yankee probably not, but we're going to sell it anyways. Okay, any questions to the wind chart? So when they give you these questions in the exam, they also will provide a wind chart, and then you know what to do with that wind chart, right? That's what you basically, and if you have a ruler, a small ruler, and thing that can actually do a right angle or so, this will really help you. So bring one along. Okay. So then there was something else we wanted to talk about. Variation and deviation. Do you remember that? What is the variation? Okay, what is variation? Variation is the difference between true north and magnetic north. So remember, where's all my variation thing? There. Okay, remember this one? So this is the North Pole, true north. It's the geographic North Pole. It's right up there somewhere in under the ice of the Arctic. And then there's the magnetic North Pole. And guess what? The magnetic North Pole is actually in Canada, which is pretty amazing. I always say we should really charge anybody using a compass sort of a fee for using our magnetic North Pole, right? Worldwide. Okay, and therefore, depending on where you are, there is a variation. So if you're in out here in Newfoundland, and you look at the geographic North Pole, it's this way, and you look at but your compass is pointing this way, and that difference in the angle is your variation, and there is variation, eastern variation, western variation. In this case, it's west. If you go all the way over to Western Canada, Vancouver Island, and again you look up, you see the geographic North Pole here, you see the magnetic, you actually have an eastern variation. So that means your compass is pointing further to the east, where if you look straight at the North Pole, your compass is pointing east of north. Here your compass is pointing west of north. So this is what this east and west is. Okay, and then of course, if you, for example, go down right here, there is a line where those two align and there's no variation because somewhere it has to switch from east to west anyways. And so the variation changes with location, and there are lines in the chart. And these lines are called the isogones. Again, iso equal variation. And at some point where there's a line with the variation 0, and that's called the agonic line. Okay, now I have another picture here that shows this better. So here again are these are the isogones. So down on this line, the variation is all the way. So this goes through Toronto, 10 degrees west or minus 10 degrees. So basically, if you're pointing at your compass needle is pointing to the North Pole, then your true reading is if you want to go from true to magnetic, you have to make an adjustment of minus 10 degrees. Okay. Now, if you want to go from magnetic to true, you have to make an adjustment of 10 degrees. Sorry for that. And this changes with depending on where you are. The green line, that's the agonic line. There is 0, right? And then we're going to the other way, where it is actually eastern. This is western, the blue lines, and the red lines are eastern variation. And to make things even more complicated, over time, these isogones, they wander, so they change. For example, Kitchener Airport used to have runway 26, and now it's runway 25 because it's a magnetic north, and the variation changed by a degree. So I'm not sure if it was 25 and now it's 26 or the other way around, but I know it's changed. So to sum it up, we have isogones, we have western deviation, western variation, eastern variation, and in the middle we have an agonic line where it's 0. And the agonic line moves around too, right? So that's what we have. And good. I think that, let's see if we have anything else. Oh, yeah. Do you remember we had on the last time we had we were talking about great circles, right? And rhumb lines and latitude, longitude, meridians, and all these things. Do they make sense? Do these terms make sense to you? Yeah, I see somebody nodding. So, Reg, do you want to give it a try and tell us? You have to turn your mic on.
I've had too much mic time tonight. Somebody else is going to have to.
Okay. Who else is nodding? I gotta see you. Okay, I don't see anybody. Everybody. Yep. Oh, Doug.
Georg, you didn't go through deviation. You went through variation,
Yep.
but you didn't go through the deviation.
Not the deviation yet. The deviation comes next.
Oh, okay, sorry. All right, so
Yep.
the different lines, the
Mhm.
rhumb line is on a flat map, would be a straight line.
Yep.
The great circle, it would be on a globe, and it's the shortest distance between 2 points on Earth, which doesn't look very good on a flat map, but it is the shortest distance. And the other one,
The other one was a meridian. What is a meridian?
the meridian, that one I'm not sure. Is that a longitudinal line?
Yeah, it's a longitude line. Right.
Okay.
Okay. Well, let's look at this for a moment. I put a little presentation there together. Okay, so the Earth's coordinate system is basically made up of longitudes and latitudes. So the longitude line, they go from the North Pole to the South Pole. So they only go around half. And then there's on the other side, there's the opposite line. So the 0 line here, which goes through the town of Greenwich in near London, which is pretty much the center of or was when this was established, was the center of the world. And so that's why the prime meridian, it's called the prime meridian, but it's basically longitude 0. And on the other side, the other half would be 180. Okay, and then we go basically east, 10, 20, 30, 40, 50, or west. So we are always in western longitudes. Okay. And these lines are known as meridians. They run north-south, basically from pole to pole. They're furthest apart in the equator. So basically they get closer, the more you come up to the pole. They cross the equator at right angles, and they lie in planes, like if you would cut through it, that sort of pass through the Earth axis. And they're basically, because they go through the Earth's center, they are halves of great circles. We will come to great circle later. Okay, so now let's come to the latitudes. The latitudes are a little different. They're basically sort of like slices that were taken off from the globe, like at the front, and they start at 0, and these are always degrees, 0 at the equator, and then they go up at 90 at the pole. They're always parallel to each other. Remember, the meridians or longitudinal lines are not parallel. They sort of all converge at the poles. The latitudes are always parallel. The 0, the equator, is the biggest one. And they also cross the meridians at not just the prime meridian, at right angles. Okay, and then towards the poles, these circles are getting smaller and smaller. And how are these numbers established? They're established basically, you measure from the center of the globe. If you go straight out, this is 0, this is the equator, and then you basically measure angles up to 90 degrees, the poles. So, but this is how they establish what is 10, 20, 30, 90 degrees. Okay, so the latitudes, they vary from 0 to 90 north or 90 south. So anything below the equator has southern latitudes. Anything above the equator in the north is northern latitudes. And anything west of Greenwich has western longitudes, and anything east of Greenwich has eastern longitudes. Okay, so this is what this whole picture looks like. And then every point in the world on the globe can be defined with its coordinates. It starts always with the latitude and then with the longitude. So this point would be 40 degrees north. Here, there's also, with the latitudes, there's always north or south. And it is 30 degrees west, because we're going from the prime meridian, we're going to the west, 30 degrees, and this is that point. And then, of course, these are degrees, and every degree breaks down in 60 minutes. So half a degree would be 30 minutes or so, and every minute breaks down in 60 seconds. And you can give a latitude in degrees, minutes, and seconds, but more common is that latitude coordinates are being given in degrees, minutes, and decimal minutes, basically. Let's say 19 point blah, 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 blah minutes, instead of going into the seconds as well. Okay, and so if you look at the SOSA website, the SOSA coordinates are on the website in location. And this is how it's defined in latitude and longitude. Okay, so this is actually pretty good explanations about in Britannica there about this. Now the Great Circle. So Doug told us the Great Circle is the shortest connection between 2 points on a globe. So it is, the Great Circle is a circle that goes through the center of the Earth, and where it sort of runs along the surface. If there are 2 points on that circle, this is the shortest connection of those 2 points. And if you then project the whole ball or the globe on a flat map, then of course it doesn't look like the shortest connection anymore. It looks different. So this would be a great circle line. And if we go a little further here, so if you look at the top here, this is a so-called Mercator or Mercator projection, which keeps all the longitude lines parallel. So there is basically, you cannot have this near the pole because it gets totally out of whack. But what this kind of projection shows you is that the angles, if somebody would sit here in China and say, which angle is it to go to San Francisco? The angles are all pretty constant. Other projections, which, for example, this here is sort of a 3D, shows more a ball. The angles don't fit anymore, because you see how the longitudinal lines are not parallel anymore. They're basically all converging towards the pole. And there it looks much more like this could be the shortest line. But if you look at this on this map, the Great Circle is this thing, and you go from San Francisco to Bangalore. And you go, how can this be the shortest line between those 2 points? But it is. To go a little less extreme here, this Great Circle thing becomes more extreme the further north you go, because eventually we'll fly over the North Pole, right? And I remember a flight that had to Shanghai from Toronto, and the plane takes off and heads straight north. And I'm going, no, 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 it's actually to the left, right? Goes straight north, flies along the east side of Hudson Bay up, right over the North Pole, over to Russia. I saw Lake Baikal and into China. That was the shortest way to get there. When you think, well, it should fly versus towards San Francisco and then this way across the Pacific, right? Okay, so what this shows us let's look at this map first. So this is, you see the parallel longitudinal lines. So it's a Mercator projection again that goes really haywire in the north. And we want to go from Havana in Cuba to Lisbon. The blue line, so if you're a naval captain or you want to fly there with your airplane, you basically take you make a line, a straight line from there to there and say, well, this is the way I go. And this is the rumb line. And the definition of a rumb line is that it crosses all longitudinal lines, all meridians at the same angle. See, the angle when it crosses the meridian is always the same on this map. But in reality, the Great Circle line, the short one would be this one, the red one, is the Great Circle. The blue one is the rumb line. The red one is the Great Circle, which is the shortest. Now they're not very far apart. They're not as far apart as the previous chart I showed, because we're closer to the equator, not really far north. So there's not such a big difference. Now, if you have a different chart, different projection, you see here the longitudinal lines are converging to the north, and in our aviation charts, this is similar as a similar projection to this. So in our charts, aviation charts, the longitudinal lines are not parallel. I mean, they almost look parallel, but they are not. And there, if you fly the rumb line on this projection now shows actually like a circle, and the Great Circle line still shows not a straight line, but it's pretty close to a straight line now, and not far from it, right? Whereby the rumb line is now quite a ways away from it, right? And again, it has to do with if you cross all these meridians at the same angle, with this projection, you're getting a funny line. So that's what this is all about. And so let's say you like rumb lines and you make yourself a rumb line and you fly on the rumb line. Where do you end up? If you follow a rumb line all the way with a heading sort of that is somewhere between northwest and northeast, then you end up on the North Pole. If your heading is somewhere between southeast and southwest, you're ending up at the South Pole. If you just keep on flying, you're crossing every one of those meridians at the same angle. Eventually, you're ending up at the North Pole. You're better, the angle is always the same. Okay, so what you to take away from here is rumb lines is basically if you put a line on a map and fly from A to B, and if it's a short flight, if it's a 50K flight, it doesn't matter. If it's a 300-kilometer flight, it still doesn't matter. But if you fly from Toronto to San Francisco, it's probably better to do a little bit of a Great Circle deviation, and it saves you some fuel. In gliders, we don't have to care about this because we follow the clouds. But for the exam, you need to know. Okay. Are we good with that explanation? Okay, then we'll end the slideshow, go out, And yeah, then we start with our, oh yeah, one more. Now we do this some other, yeah. Doug, you talked about the deviation. So when we, and where this all comes out, if we measure a heading or a course on the map, then this is to true north, because we are measuring on a basically the angle. Losing my voice here. We're measuring the angle between one of the meridians and our course line, and but in the end we want to know what compass heading to fly, right? So first of all, once we have our true track established, then we have to say, okay, now I want to put the variation on to get my magnetic track. And then that's not quite right yet, because every compass that is installed in an airplane has slight errors, and that's called the deviation. So we have the variation, which is the difference between true north and magnetic north, and that can be pretty large. Like in our area right now, it's about 10 degrees. In other areas, it can be even larger. If you get closer to the poles, there's actually an area where you just cannot use a compass anymore. So variation, difference between true north and magnetic north. Deviation is basically the error of the compass, individual compass installed in the individual airplane. And that gets established by swinging the compass. I think we had that term in one of our questions. What is swinging the compass? And then this gets done typically every year or second year at the annual. And then the guy who does that will put a deviation table. The compass usually has a little room for a chart, for a little, not a chart, but a sort of a note and a table, and puts a table of deviations onto the compass. And then it says, for this heading, steer this heading. And that's the deviation table. So we have variation, deviation, and so on. Okay. And to finish this off quickly, let's see if I can find this quickly. Sorry for that. Here we are. No, that wasn't the one I was looking for. We do this next time. It's takes too long to find this now. I thought I had it. So if we take a quick look at this thing, it's basically to go from true to compass. You can sort of have a table like this. This is the true heading or the true track you want to fly. You put the variation on. Then you get magnetic. Then you put the deviation on, and you get the compass. This is how this works. And there's so you can remember this. Remember, TV makes dumb cadets. You go true, variation, magnetic, deviation, compass. TV makes dumb cadets or dumb children. Up to you. If this cadet thing offends you, then TV makes dumb children. So TV make. Can I make this bigger? No. Can you read that? TV makes dumb cadets. So true variation. So TVMDC. That's the way it goes when you go from true to magnetic or compensating. And if you go the other way, from compensating to true, the other way, of course, with different instead of minuses, this will be pluses. And the other thing we need to know when we go from left to right on this table is east is least and best is west. That means Western variation and also deviation, you add. So you basically add this to the true to end up with the compass. If you have an Eastern variation and deviations, they have a minus. So east is least and best is west. Just remember that. That helps you remember that when to use a minus and when to use a plus. But we will go through questions where we sort of have to look at this. Okay, let's go into test questions. I'll put this away. So this be it. Can you see it well? You can make it a little bigger. Nah, that's okay. Okay, I need another one. Okay. So here's our question. I gotta go all the way to the beginning. Does anybody want to have a water in, water out break? Or should we keep on going?
I'm going to grab something, but if everyone else wants to keep going, that's fine. I've got my earphones in so I can hear it even if you don't see me at my.
Okay. Or well, let's see. Greg is getting up, so let's have a quick break here. So I brought a different plane today. Okay. Okay. Greg's still away. Okay, Jimmy. Brad's away and Noah is still away. Okay, everybody back. Reg is not back yet. Brad, are you there? Okay, Reg. Okay, we'll get started. Okay, so question number 1. Spoilers. Remember spoilers? We just talked about those. In this case, they mean air brakes on a glider. Are designed to A, decrease drag and decrease lift? Yes or no? No. Increase drag, increase lift? No. Increase drag, decrease lift? Sounds about right. Yeah. Or the other one is decrease drag and increase lift? No. Okay, so C is obviously the correct answer. Okay, so next one, the angle of attack. Oh, sorry guys. Here we are. The angle of attack is defined as the angle between the chord line and the what? Do we know what the chord line is? Who knows what the chord line is? Hands up, guys. Ladies. Okay, I see. Doc says yes. Okay, so the chord line is on an airfoil, and I'll show this in a minute. The line from the leading edge to the trailing edge, that's the chord line. And so the angle of attack, I'll bring up, and it's in Mark's okay, so see this? So this is the chord line from the leading edge to the trailing edge. And the relative airflow, basically the airflow as it hits the airplane, and the angle between those is the angle of attack. And when that gets too big, so if this rotates up and makes it bigger and bigger and bigger, then at some point it'll stall and the lift will collapse. Okay, so we'll go out, put this aside again. Okay, so let's see what options we have. The angle of it between the chord line, we know what the chord line is now, and the what. Let's see, true horizon, no. Longitudinal axis, no. Relative airflow, yes. That's the one. Horizontal axis, no. Okay. We're going to question number 3. Longitudinal stability is what? Pitch stability, roll stability, stability around the lateral axis, both A and C. Okay. Any guesses? You should know that now. Remember the axis. Here's my airplane. I'm flying a biplane today. Is stability like this. An airplane that is longitudinally unstable is flying like this, up and down. So the pitch is not stable. So it is called pitch stability. But is pitch stability the right answer? Now we have to look at the others. Is it also roll stability? No. Is it stability around the lateral axis? What is the lateral axis? Remember, the lateral axis is the one along the wings, and we are rolling around the lateral axis if we do this. So yes, this is also correct. So the correct answer is D. That says A and C is correct. So again, when you write the exam, don't just log in on or focus on the first answer that this is correct and say and carry on. Read all the other answers or the options that are given. Okay, longitudinal stability is influenced by okay. So the options is the size of the horizontal stabilizer. Dihedral, do we all know what the dihedral is? Dihedral is basically when the wings are like this. So the wingtips are a little up. And it helps, dihedral helps with roll stability. Makes the airplane more stable against rolling. Okay. And do we know what sweep back is? I have to get my other airplane now. That's basically the wings being swept back, like in airliners, fighter jets, and all these kinds. So that's the sweep back. And do we know what the keel effect is? It's probably something that has to do with the yawing thing, right? Because if this is holding it straight, I'm not even sure if this is a real term. But anyways, the answer.
Jorg,
Yeah.
pardon me. It is, but the keel effect refers to the rolling with the fact that when it's sliding, it wants to return to level flight because of the additional friction and weight of the center of gravity. So it's most all the things I've seen illustrated with a high wing airplane.
Okay, good. Okay, thank you. I didn't know that. So in our case, so the longitudinal stability, keep in mind it is basically like this stability. So obviously, the horizontal stabilizer has something to do with it. Imagine there's no horizontal stabilizer. The thing would go either this way or this way, right? With the horizontal stabilizer and the elevator, you're controlling the pitch and the longitudinal basically attitudes and so. So that's this case. It is A. That is the correct answer. Okay, and so the pitot tube. Do we know what the pitot tube is? You should all know this by now. That is the tube that measures the airspeed of the airplane. It's basically a tube that sticks out the front. And when we are moving through the air, there's additional pressure in that tube. And that goes into the airspeed indicator and gives us the airspeed we have. Okay, so the pitot tube provides what? What's okay? Give me fingers up. What of the answers you like? Number 3. I see number threes. 3. Okay, Noah 3, agree, good. Jimmy, yes, of course, right? Okay, yeah, that's the pitot tube. Dynamic pressure, so they also call this dynamic pressure. Static pressure is the regular air pressure. Dynamic pressure is the pressure when you're moving into the wind, and that's what the pitot tube measures. It could also be called the ram air pressure or something like that. But dynamic pressure is the technically correct term. Okay, the movement of an airplane about the normal axis is called. So do we know what the normal axis is? Okay, I see. Okay, I saw some threes up. Are we all agreeing on threes? Yes, it's yawing. Yeah, its normal axis is the one that is vertical, and yes. Okay. We're already moving faster now. Okay, the vertical speed indicator is susceptible to what error when the aircraft levels off from either climb or descent. So first of all, we need to know what is the vertical speed indicator. In our language, in glider language, it's the variometer. It shows us the speed going up and down. And the right answer there is, so it's position, it has nothing to do with the position. Pressure, what would it have to do with the pressure? Compressibility. Compressibility is something we talk about when we are getting close to the speed of sound. This is when the air becomes compressible, but it's with gliders not a factor. It has, and this is a typical power plane question. It has a bit of a lag. So when you climb at a certain speed, like 500 feet per minute, and then you level out, it takes a little while for the variometer or the vertical airspeed indicator to settle at zero. Glider variometers, they are much more sensitive and much quicker in the response. So for gliders, it does not really, A, it doesn't matter, and B, it does not matter for gliders. And B, it's the lag is very small. But yeah, okay. Okay, number 8. What altitude is read from an altimeter when the barometric scale is set to standard barometric pressure? So do we know what, okay, I see already numbers up. Okay, yeah, Reg, you're right. Do we know what standard barometric pressure is?
29.92 inches of mercury.
Yeah, do you know it in millibars too?
No, but I know where to find it. My notes from our last meeting.
Okay, it's yes. So the standard barometric
13 or something like that.
it's 1013.2
There it is, 1013.2
millibars or hectopascals, as they say today. There is the standard altimeter setting is basically when in areas where first of all high up, because it doesn't matter anymore if you're a little higher or lower in avoiding, let's say, mountains and this kind of stuff. And secondly, when the air traffic control wants to eliminate the changes of air pressure over distance, and they control a large area, so they say, okay, everybody set their altimeter to standard, which is 2992. And then everybody has the same altimeter setting. It doesn't matter if they're flying in an area that has higher pressure or lower pressure. And that means their altimeter all show the same. So if he says you fly at flight level, and then we talk about flight levels. So you fly at flight level 210 and you fly at flight level 230. They nicely sort of they miss each other, and they have a nice vertical separation, and it's always the same because they all have their altimeters set the same. But of course, this doesn't work when you need to land, because when you need to land, then what really counts is how high above the ground you are. And this is when you set your altimeter back to the actual pressure. And they give you this when you're sort of approaching, let's say, Kitchener. They give you the altimeter setting, as they call it, which is basically the actual pressure, which when you touch down shows the airport elevation on your altimeter, theoretically. For the SOSA, this would be our 850 feet. Okay, so
It's actually D, the answer, because flight levels use pressure altitude.
flight, yeah, it's B, yeah, right. The right answer is D, because it's flight levels and pressure altitude. So for whatever reason, this is one thing I had to read over twice, is why does standard barometric pressure translate into pressure altitude? In my mind, it would have been called standard pressure altitude, but it doesn't. It's pressure altitude. So that's the term for it. And there's another term you need to know to pass the exam, and then you never ever need to know this again. You can forget it. Okay. An airplane which is stable by design may become okay, unstable in a certain way, right? Laterally, longitudinally, or so on, due to changes in of the what? So what we all know is what can we easily change in an airplane? We can change the center of gravity. Let's say we drop our water, or we put somebody in the cockpit who is way too light, right? That kind of stuff. So the center of all the other things, they're pretty much built into the airplane, like the size of the tail, the vertical, the horizontal stabilizer, and so the thing that's pretty is pretty movable or variable is center of gravity. Depends on the loading, and you can even change it in the air by dumping your tail water or something like that. Okay, so I would say we're talking, and what is this instability when the center of gravity changes? It's the longitudinally unstable. So let's see what offers center of gravity. This offers center of gravity. This offers center of gravity. Directionally, definitely not. The center of gravity doesn't matter here. Distribution of weight directionally, no. Longitudinally and center of gravity, that's it. So it becomes longitudinally unstable due to changes in the center of gravity. That's the right answer. So B is the right answer. Okay, you all knew this, right? Yes. Okay. Okay. Oh man. The primary members of a truss type fuselage. Ay, ay, ay. I have a picture. I'll send you the picture. Our fuselages in modern gliding, they're all shells, right? So they don't have these members. But in the old days, there is airplanes have spars that are in the wings, right? They have ribs that are in the old days, they had ribs in the wings. You can still see it in the Citabria, right? It has ribs. They have formers, you don't see those, and they have longerons, which is basically longitudinal members that sort of describe the fuselage, and in this case, it is the longerons. I will look up if that answer is correct. Just hang on here. So 10. Yep, D is the correct answer. Okay. Yeah, it's another thing you basically never need to know. Okay, so but Longeron, keep that. You never need to know this for the real gliding, but for the exam, you may need to know that. Okay, air flowing over the upper surface of a wing tends to flow inwards faster than the air flowing over the lower surface, neither A nor B, or both A and B. Okay, I see 2. Yes. Any other ideas? I see another 2. And you both failed the question because the correct answer is
A and B.
Yeah.
I thought that it moved going over the wing, and I was trying to think which way would it go, and I just thought the outbound wing would go faster, so that it might be sucked that way. I reasoned incorrectly.
Yeah. So we all know it flows faster over the top of the wing, right? So this is B. We all say is correct, and you all said yes, it is B or answer 2. But on the top of the wing, it also tends to flow inwards because we have these vortexes, right? From the bottom of the wing, it flows outwards and forms this vortex at the wingtip. And that makes the air flow inwards on the top of the wing. Slightly, not much, right? But it is, in this case, it is really D. So be careful if you don't jump too quickly to an answer. Read them all and say, can it be that it's flowing inwards? And yes, it does a little bit. Okay. A wing has a span of 52 feet and an average chord of 8 feet. It has a wing that has a span of 52 feet and an average chord of 8 feet has what does it have? What's the ratio between span and chord? I see 3. Yes, 3, 3, 3. It has an aspect ratio. So we know we only have two answers with aspect ratio. The question is it 44 or is it 66.5? And yeah, I see somebody saying 4. So what you do is you divide basically 52 by 8 and you get to 6.5. So aspect ratio is basically span divided by average depth of average width of the wing. And a glider, just to let you know, a modern glider, like an 18-meter ship, they have about 30 aspect ratio, right? 6.5 is, I wouldn't even call a glider. Okay. Anyways, so aspect ratio is wingspan divided by chord. And anything that puts wingspan and chord into relation is aspect ratio. These are the 3 things you need to know. Okay. So a stall occurs when there is no longer sufficient what to counteract the what of the airplane. Okay, remember all these forces we have on the airplane? We just looked at this the other day, earlier. And so what is an airplane? What keeps it up is the lift. And what drags it down, what makes it want to go down is the weight. So basically we look at the answers. Obviously lift is important. Weight is also important. So let's look for lift and weight. There's one answer that says lift and weight in there. Drag has nothing to do with this. Thrust has nothing to do with this unless you go vertically up in a jet, then it has something to do with it, but not in a glider. And so weight and lift only appears in one answer, and that's B. Okay. All clear or any questions on that? No. Pretty simple, right? Okay, select the correct statement. Okay, read those over. Spars are cambered to form an airfoil section. Spars are connected between the leading edge and the trailing edges of a wing. Spars are intended to stiffen a wing to reduce twisting. Spars provide a suitable framework for the wing covering. Ooh. Okay. Okay, interesting. Lots of strange answers. Okay, do we know what a spar is? Spar is basically a structural element that goes out into the wing. Today's airplanes, they only have one main spar, and that the torsion of the wing is being taken care of by the skin around it, like a tube. So that's what in today's airplanes what we have. But older airplanes, for example, the Citabria, it has two spars. It has the main spar that keeps the wing from breaking off, and then it has a second spar that keeps the wing from twisting. So number C is certainly they're not cambered to form an airfoil section. They're not connecting leading edge and trailing edge of a wing because the spar runs along the wing, not horizontal, not 90 degrees to it. And spars are intended to stiffen a wing to reduce twisting. Yes, in old airplanes, yes. Nowadays, no. Spars provide a suitable framework for the wing covering. No. And we also don't have covered wings anymore in gliders. So it's 14C. So the really correct answer for this would be the spar is taking the bending forces of the wing. So what keeps the wing from just bending up and breaking off, that's the spar. That would be the really correct answer. But anyways, so here they are also, in some airplanes, spars are there to stiffen the wing and reduce twisting. Not in our current airplanes anymore. Okay, so next one, 15, select the correct statement. An aircraft accelerating in a climb is in equilibrium. Well, if an airplane is accelerating, then it cannot really be in an equilibrium. An aircraft in straight and level flight at a constant airspeed is in equilibrium. That sounds about right to me. An aircraft which is turning at a constant altitude and constant airspeed is in equilibrium. Not so sure about that.
I'll say no.
An aircraft accelerating, anything accelerating, it cannot be in equilibrium. And an aircraft...
Accelerate, Jorg.
Yep. Say again?
That's why you feel G's, because you are accelerating as you turn.
Yes, and a turn is also accelerating, so it's basically just the straight and level flight. Nothing changes, everything is staying the same. That's a nice equilibrium, and that is the right answer. The turning is also, you're correct, is also an acceleration. Yep. Very good. Lift acts 90 degrees to what? We talked about this. We said 90 degrees to the airflow, right? Okay, and that's by definition. Okay, 90 degrees to the chord line of an airfoil, lateral axis of an airfoil, relative airflow, or the angle of incidence now. Okay. We know what the chord line of an airfoil is, right? We talked about this. We know what the lateral axis of an aircraft is. We talked about this. We know what the relative airflow is. That's the airflow the airplane experiences. And that's in this case, the correct answer. Number C. And we know, do we know what the angle of incidence is? Yeah, Reg knows it. Everybody else? No, it doesn't. The angle of incidence is the angle of the chord to the longitudinal axis of the airplane. So that's a little difficult to picture. So if you look at the longitudinal axis, is basically this airplane doesn't help me here. Is basically going through the airplane from the propeller to the tail, and the chord can actually have an angle here, and it usually has an angle, and that angle between the longitudinal axis and the chord of the airfoil, that is the angle of incident, and that's an angle that's built into the airplane, so that never changes, unless you crash it, then it changes. So it's other angles, for example, angle of attack changes all the time as you fly, but that is an angle that is basically built into the airplane. And if that angle of incidence is, for example, not enough, then it's maybe very difficult to get this airplane off the ground, because the wing is just not providing enough lift with the tail and the main wheel on the ground to get this beast off the ground, right? So sometimes this is one reason for an angle of incidence. Okay. So keep that in mind. We'll see if I can find an illustration to that, and I'll send that out. Okay. Then 17, stress is many things, right? So force which exerts a strain. Okay. That's interesting. Let's read on. Distortion due to strain, no, it's not stress, right? Strength, no. Corrosion, no. So the only answer that makes some sense to me here would be a force that exerts a strain. Let's see what the answer sheet says. 17. Yes, A. So basically, and I mean, this is so wrong. Stress is not a force, right? Normally, if you put a force on a piece of equipment or on a wing, then certain components in that wing will be stressed. There will be stressed in there. So, but stress in itself is not a force. But in this case, that's how they see it. Whoever wrote these exams sees it. So it's if you're confronted with a question like this, just go through the ones. I mean, it's clearly not corrosion. It's not strength. And then you can eliminate a lot of them. It's not distortion, even though we're getting closer, right? Right, by eliminating all the ones, it's certainly not. I arrived at the A. I didn't really know either. Okay, you can't really explain it either. It's from an engineering point of view, just not correct. Okay, now we are coming to the dihedral. Remember we talked about dihedral is this? Okay, it's the angle which each wing makes with the horizontal. That sounds already like a pretty good answer, right? The difference between the angle of attack and the angle of incidence, definitely not. The angle between the lateral axis and the sweep back, no. None of the above. Well, the angle with which each wing makes with the horizontal is the dihedral. There is a nice point.
So is the horizontal synonymous with the lateral axis?
Yes, yeah. In this case, I think it's basically sitting on the flat ground, right? The horizontal, but it's also the horizontal is also the lateral axis, right?
Yeah. Okay. Thank you.
Yeah, and there's a nice picture in the FAA handbook about dihedral, and also it's in the same page as also aspect ratio. Like it shows high aspect ratio, low aspect ratio, and then in the same page is also dihedral. So if you look into this and search for it, you don't have to go very far. You'll find that. Okay, but dihedral is basically wings going up a bit. Do we know why it is there? What it does? It gives more stability, roll stability. This is roll stability. So stability around the longitudinal axis. When the wings have a little bit of a V, then there's more stability that way. Many Russian airplanes, like Russian airliners, they have a negative dihedral. The wings are hanging down, right? I wonder how they fly. Okay. So dihedral is something good for you to know. First of all, it comes up in regular conversation, and it will show up probably on the exam in some form or another. Okay, relative airflow is, that's interesting. Is parallel to the flight path of an airplane. Yeah, this doesn't looks pretty good. Parallel to the horizon, no. Opposite the flight path of an aircraft, yes, that's actually the true one, because the relative airflow is the other way. When you fly, you have a headwind, right? Obviously, so it's opposite to the flight path, if you assume the flight path has a direction. And both A and C, well, it's parallel to the flight path, yeah, and it's opposite to the direction, really to the direction of flight. Okay, and A and C is the right answer. So D is the right answer. Okay, so again, don't get stuck on the first answer. That sounds about right. Okay, the position of an airfoil where the boundary layer changes from laminar to turbulent flow is called what? Does anybody know? Doug knows. Okay. Okay, so it's let's go through the what's on offer here. The reference point, no. The reference point when we talk about an airplane is actually the datum from which we measure the moment arms for center of gravity, and that's usually at the leading edge where it meets the fuselage. That's the reference point. So it has nothing to do with where the boundary layers on the wing. Okay, delamination point is doesn't exist. There is no such thing as a delamination point. Transition point, yeah, it could be a transition point. And separation point. So somebody said one. Yeah. Okay. I would say it's the transition point, because with the boundary layer changes from laminar, it transitions from laminar to turbulent. The separation point is when you stall, where the airflow comes off the wing, leaves the airfoil. Okay, so
But isn't a laminar flow where it is, it's attached to the wing and then separates?
no, it just flips over to be turbulent because it runs out of energy, right? And the idea is, in the old days, the airflow was always turbulent, but with laminar airfoils, one tried to get as much of the airflow laminar for as much of a length, also along the fuselage. And along the fuselage, the airfoil is laminar to about where the window is, the canopy window, and then it flips to turbulent. The longer laminar stretches you have, the less the less drag. And there is it is a transition, right? So in my mind, the transition point is the correct answer. I'll look it up. 20B, yes, transition point. So it's a transition. There's nothing bad that's happening there. It just transitions from laminar to, it's typically on the wing. It happens past the spar where the wing gets narrower again. So as the wing gets thicker, the airflow likes to lay there pretty thin. But there, when it goes over the thickest point, where it gets thinner again, this is where it flips over to laminar, flips over to turbulent. Okay, and this is if you have lots of bugs on the leading edge, then this happens earlier. The boundary layers gets turbulent much earlier because every bug is a disturbance in the laminar airflow, and there's turbulences already coming off it, and they make the whole wing at some point turbulent. So that's why we don't want to have bugs, but we have to wash off all the bugs we have on the glider every morning. Okay, otherwise you will lose $30,000 of performance if you don't wash the bugs off. Okay, 21. The rate of change of temperature with height is called, hey, we talked about this today, right? Is called, we all know what it is, right? The lapse rate. Yeah. Not the inversion. We also know what the inversion is, right? We talked about this too. This is when the temperature actually goes up, and it's just a small area, right? Advection, no, and convection, no. There is no such thing as a convection rate, but it is the lapse rate. Okay. 21C, yeah. In an isothermal layer, the what remains constant? Well, that's pretty clear, right? Iso means the same, right? Greek. We all remember Greek in school, right? I hope. So what remains constant? Isothermal. That means equal thermal, equal temperature. So what remains constant is that temperature, B. No, not the temperature and pressure. Temperature and no, not either. It's temperature. 22B, yes. That's pretty easy, right? Nothing needs to be explained there. Okay. '23. Okay, some movement of air warmed by the Earth is called. Ooh, okay. Okay. What happens to air when it's warmed by the Earth? It becomes a thermal. Okay, see what we have. So when there's warming in there, is quite likely it's vertical movement, and so it's horizontal deflection doesn't mean anything much to me, anyways. Vertical advection, no, there's no such thing as vertical. There is advection, is basically a thing called cold air advection, when more cold air is sucked in behind a cold front. But it has nothing to do with the warm air. So there's horizontal convection. The horizontal movement of the air is not called convection. Convection is always vertical. So vertical movement of the air warmed is convection. So if you have read my W-axis, you know this, right? Convection is good. That means we can fly. Okay, 23D. 24. The neutral region between two high pressure and two low pressure areas is called. I have a drawing for that, and I'll send you that. So It's basically if you imagine high pressure system is a hill and a low pressure system is a valley, and that now if you have two high pressure systems and two low pressure systems, then you get sort of a kind of a saddle in between, right? And it's pretty sure it's called a col. Yeah.
Berg, if you love the mountains, you will know that this term is also used in the mountains for a saddle-like shape of.
Yeah. And it's quite often the pressure picture is the analogy is basically highs and lows like in the mountains. That's why we talk about a high pressure ridge and a low pressure trough and end, right? And yeah, that's why between that it's a call. Yeah. And it's, I mean, again, this is something you only need to know for the exam, never later again. But it's a good thing to know. And I have actually I should make a note to send that out to you. Okay, so the 25. When an air mass is what? And no new water vapor is added, the relative humidity will. Okay. So the air mass can be heated or cooled. This is and the relative humidity can increase and decrease. Okay, so let's try this first. When an air mass is heated, the relative humidity will then, if the air mass gets warmer, it will decrease because as the air gets warmer, it can hold more humidity, so the relative humidity will decrease. The relative humidity means a percentage of how much water how much humidity the air can hold, or water vapor. So okay, so heated and decrease we have, and so this heated. Okay, there's no heated, and so then when it's cooled, when the air mass is cooled, the humidity will increase. We have cooled and increase. And cooled and decrease? No, it is cooled and increase. B, 25B, yep. Okay, so if you cool an air mass, then the humidity goes up. And in an extreme case, it'll form fog if you cool it far enough. That's how you can remember it. And if you heat it up, it gets drier and drier and drier. Okay, 26. The air mass may be defined as a large section of the what? With uniform properties of and in the horizontal. Okay. Interesting. An air mass may be defined as a large section of, let's see what we have. We have stratosphere, troposphere, atmosphere, and troposphere again. And what are the properties of an air mass? Do we know that? Anybody? An air mass is defined by, the properties are temperature and humidity. That defines an air mass. Okay, and typically, so an air mass may be defined as a section of, any ideas of what they're talking about here?
Atmosphere?
Atmosphere, yep. Atmosphere, definitely. And with uniform properties of, we said, temperature and humidity, right? See if we have this. Atmosphere, stability, moisture. Okay.
I had D.
D, the troposphere. Do we know what the troposphere is versus the atmosphere? The atmosphere is everything that the whole mantle of air that goes around the Earth is the atmosphere. The troposphere is the lowest part. That's basically where all the weather happens. The above it is the stratosphere and all the other things. So D is the right answer because it's happening in the troposphere and temperature and humidity. So 26D is the right answer. Now, in the real exam, not all the questions are like that, right? It's I guess somebody would like to do it this way. Okay, when air subsides, what does it do? Does it compresses and warm and get warmer? Does it expand and cools? Does it expand and warm? Can this be that an air expands and warms? Cannot be. If an air mass expands, it always cools. If it compresses, it always warms. So C is definitely out. Remains constant in temperature and density. No. The other thing is we need to know what subside means. Do we know that? Okay, so subside in terms of meteorology means the air mass is coming down. It's going down. And so the air mass is going down. And what does the air mass do when it goes down? It gets warmer because it compresses. And it warms. So A should be the right answer. Let's see. A is the right answer. Any questions to that? So the takeaway here is the word subside, as in far as when it comes to weather or so means, or air masses, it goes down. And an air mass that goes down compresses, and if it compresses, it warms. Okay, so 28, a front is, we know what a front is, right? A narrow transition zone between a cyclone and an anticyclone. Not necessarily. A squall line? Yeah, can be, but not necessarily. A narrow transition zone between two air masses. A wide area of cloud. So D is definitely out. So what is our answer? Yep, we have, are we seeing three fingers? Yeah. C is the right answer. We talked about this, right? There's two air masses, and the fronts in between are basically the dividing lines between transition zones. If there's a cold air mass running under a warm air mass, we have a cold front. If there's a warm air mass running over a cold air mass, we have a warm front. Okay, 28C is the right answer. Okay, now the normal time interval between METARs is, you know this now, 1 hour. Yeah, I've seen a 2. Yeah. Noah is showing a 2. Yes, okay, it's 1 hour between METARs. Okay, and the next one is the normal interval time between TAFs is. We had 6 hours, right? Yep. Okay. The normal, and now we are in weather stuff. The normal interval between area forecasts is, what is it? Yep, I see D4, yeah. It's 6 hours. Yeah, I saw you showed 6, Noah, right? 6 hours. Yeah. So area forecasts and terminal forecasts are 6 hours, and the TAFs are 1 hour. Okay. Good. The height of the cloud base can be determined from. Interesting. That's good. Surface temperature, dew point temperature, the lapse rate, all of the above. Yeah, I would go. So you can calculate the height of a cloud base by taking the difference between the dew point on any given day and the maximum temperature. And let's say that's 10 degrees. You multiply it by 400, it gives you 4,000. This is going to be your cloud base above ground. So surface temperature certainly is important in this. The dew point is also important. The lapse rate probably as well. So I would say all of the above is probably correct. Let's see, 32 is all of the above. Yep. Good stuff. Normally we do this in a tephigram, right? And the tephigram has all these things in there. It has the temperatures in there, it has the dew points in there, and it has the lapse rates in there. So yeah, with the tephigram, you can go in and determine with basically right from the dew point line and the temperature line where the cloud base will be. I could show you this. Unfortunately, my online Tephi all of a sudden doesn't work anymore. I tried to bring this up today and it said, no, we don't have this anymore. Okay, so otherwise I could demonstrate this very nicely. Okay, so as altitude increases, the wind will normally, now we are in the veering and backing again. So we're going up. What does the wind do? Well, first of all, does it change in strength? Does it get weaker or stronger when we go up? You know that, right? So it increases. And that is already pretty much the answer, right? Number C. It veers.
And doesn't it veer because there's less Coriolis effect if there's less friction from the turning Earth?
Yeah, there's it veers because there's less friction on the Earth, which interferes with the Coriolis effect. That's true. So going higher up, it usually turns to the right or clockwise. Coming down, it decreases when you land and backs, which is counterclockwise. Okay, good. Okay, now we come to the compass. Hey, given heading 123 compass, deviation 3 east, variation 10 west. Then the true heading will be what? So remember the TV makes dumb children? This goes the other way around. So it goes backwards because we are starting with the compass, right? So now we have to add this. East is least, but it goes towards the compass. In this case is now east is positive and west is negative. Okay, so we take the 123, we add 3 is 126. We take away 10 is 116. 34. Let's see if that's correct. Yep. Okay. It's of course easy to get the pluses and minuses wrong, right? So, yeah, with those two, of course, together there are 7, right? So if you add 7 to this, then you get to 130, which is wrong, right? If you cannot get to 136 in any way, so this is totally wrong. You cannot get to 126 because somehow those two have to work in. So it's basically the only answers that make possibly sense, if you don't really know how to do this, is A and D. The other two don't make sense. This is how you can also approach it if you don't know, if you forgot which way this goes, or if you forgot the TV mixed dumb children, or if you forgot that all the when you go backwards, the minuses become pluses and the pluses minuses. So anyways, so you can eliminate those two, and then if you guess, you have a 50% chance. Okay. Any question? Okay. Pilotage. I love this word. This is nice. And it's another one of these expressions you have to learn, or terms. It refers to navigation by use of items such as predetermined wind vectors and true airspeed. Not wrong. Navigation by reference only to landmarks. Yep, that's it. Navigation by use of radio aids? No. None of the above. I would go with B. So, but the A would also be the A is basically dead reckoning, and I think pilotage really refers to you're looking down, you see your landmarks, you look at your chart, and this is how you navigate. In the old days, I used to fly like this. I remember that. My wife was the navigator, and I was the pilot in a power plane. Okay, let's just see what the wisdom is. It is B. Yeah. So we guessed right. It's navigation by reference to landmarks. That's something you just have to remember. Okay. 6:36. An urgency. Oh, we're way past 9 o'clock, I see. Too much fun. So yeah, we'll maybe cut it off here. Sorry for drawing over here. I wasn't looking at the clock here anymore. Okay, so thank you very much. And there were a few things I wanted to send out. One was
My co-pilot says that we are running over time and we have to call for permission to land.
Yep.
He wants to go when we're done.
Okay. So I will send you the decoder for the weather. Have fun with that one. And I'll send you the picture of the call so you can picture what that looks like. And there was something else I wanted to send out. We'll see if I remember. Okay, I'll send this out with regular email. I think they're pretty small files. Okay, have a good night, good evening. Enjoy.
Thank you.
And
Thanks.
see you next Thursday.
Okay, thanks, George.
Thank
Thank
you.
you.
You're welcome. I'll turn the recording off and check how this came out. Okay, recording stop.